Hi, I'm Zach with HKN. This week we are we're gonna make a video about something called root locus. So this will be applicable to your systems analysis class. So what we have here is we have a transfer function set up in a closed loop configuration. So we would have, say, in a real life scenario, this box right here would be a mechanism you're trying to control. We would put it in a closed loop so that we can set a reference and then have our input depend on the difference between our reference and our output, so we can kind of see what's going on at the output. And as a designer, you would have you would put in this little value k here. That's a gain. Say an electrical system, it could just be a linear amplifier or something. So the idea is that we want to find what happens to the poles of the total closed loop system as we vary this gain k, because we have control over that. We could set it to whatever value we want. So we know from earlier in the systems analysis class that when we have a transfer function, an open loop transfer function, g of s, we'll call this box right here g of s. We have a g of s in a closed loop. We could also just multiply k by g of s right away, put them together. It's just so when we set it in a closed loop, we get a transfer function like this. We get k times g of s over 1 plus kg of s. And ultimately, we were worried about the poles of this transfer function, right? Because that's what's describing this system here. And the poles tell us quite a bit about how the system behaves. So we'd like to know, for all values of k, what the poles of this system look like. And we can do that with a root locus. And so this would be a little bit difficult to factor and follow what k does, how k behaves. So it turns out there's a way we can figure out its behavior just from some rules and from the poles and zeros of just g of s. So all right, so let's get started here. So there's 5 kind of basic rules that we have for sketching root locus. So the first one is that the number of branches in our root locus, which is the number of separate paths we'll see, is going to be equal to the number of poles in g of s. This plant here. How many poles do we have in g of s? We have s equals -2 would be a pole, s equals -4 would be a pole. There's 2 poles, so number of branches in our root locus is going to equal 2. So in what we sketch in a little bit, we'd expect to see 2 separate paths. All right, what's the second rule? Second rule is that, okay, so so we can pretty much expect that any system we're working with will be real. So in a real system, we can have complex poles, but every time we have a complex pole, its complex conjugate also has to be a pole. So what that's going to say is that, so we have a real system. So we are going to be our root locus, which is plotting the poles of this, right? It doesn't necessarily have to stay on the real axis in the real imaginary plane, but it has to be symmetrical about it. So we get symmetry about the real axis. Okay, so that means that when we're sketching our root locus, if we decide that one branch kind of veers away from the from the real axis. The other one has to do the same but opposite thing. All right. What's the third rule? So this one's a little bit tricky, but so the root locus contains has segments on the real axis wherever we are to the left of an odd number of poles or zeros that lie on the real axis. So that one's kind of meaningless until we start actually seeing what the drawing looks like. So let's just leave that blank and come back to it. What's the fourth rule? Okay, maybe this rule should have gone before this one because it kind of explains what the poles and zeros are. The root locus begins. So when we say begins, ultimately what we're doing, with the root locus, we're sketching what happens to the poles of this system as we vary k from 0 to infinity. So we'll see the values of the poles for all values of k. And when we say the root locus begins, that means k equals 0. So the root locus begins at the poles of the open loop transfer function, g of s, and it ends at the zeros. That's kind of interesting because we're dealing with a closed loop, but all the information we really need is the poles and zeros of our open loop. So the root locus begins at the poles, poles of g of s, and it ends at the zeros of g of s. Okay, so there's one more rule, but let's actually get started drawing our root locus. Okay, so let's see what the poles and zeros of this transfer function are. Well, it's pretty easy to see the poles. The denominator here is already factored. The poles are whatever values of s that result in the denominator here being equal to 0. So there's 2 of those values. If we subbed in s equals -2, this term would go to 0. If we sub in s equals -4, that term would go to 0. So the poles of g of s are s is equal to -2, s is equal to -4. Now the zeros are the factors of this numerator. And we have a polynomial that can't be factored into real numbers, but we could plug it into the quadratic formula, or just I plugged it into my calculator and had it factor it. So what this factors do is that the zeros of g of s, they they're complex numbers, but there's only 2 of them, so they have to be complex conjugates, right? So what this factors to was 2 plus and minus 4j. Okay, so now we have starting and ending points for our root locus. So I guess we could just get started drawing it here. So the root locus, we sketched the root locus in the real imaginary plane. Okay, so what did we say? We said that our root locus is going to begin at the poles of g of s. So let's plot the poles of g of s to this graph here. Poles are at -2, s equals to -2. Let's say that point's -2. This point's -4. So we usually denote a pole with a little x. And let's also plot the zeros. So we know that, so we have complex values here. We will go to a real, we'll have a real component of 2. Let's say it's about here. And then there's 2 values here. There's 2 plus 4j, 2 minus 4j. So we'll go up to plus 4j. We denote zeros by a little circle. And we do its complex conjugate down here. Okay, so now we have our starting and ending points. Let's see if we can get anything else from our rules there. Okay, actually, yeah, let's talk about this rule I left blank. So the root locus has segments on the real axis. Real axis segments to the left of an odd number, any odd number of poles or zeros that lay on the real axis. To the left of odd number of poles or zeros. Okay, so what does that mean? So we will start over here, and we'll just follow our real axis, looking for poles or zeros that we drew in that lie on our real axis. Every time we're to the left of an odd number of them, we can know for sure that that segment of the real axis is part of our root locus. So let's do that. We follow this. We're at 0, 0. These don't count because they're not lying on the real axis. We're at 0, and here we get to 1. So we're at 1 pole there on the real axis, and then here we get to 2. So to the left of this odd number, 1, we can fill in up till we run into another one and we have an even number. Then it's not part of it anymore. So we know that this whole segment right here is going to be part of our root locus somehow. We don't know. I guess we don't know exactly. We have a pretty good idea, though, what's going to happen. Okay, so there's one more thing. So in a lot of cases, most cases I'd say, the order of this numerator, see how we have an s squared up here, and this, if we multiply it out, would also have an s squared. Usually the order of the numerator in our g of s won't be equal to the order of the denominator. So we'll have a, in most systems, we'll have more poles than zeros. Well, I guess we could have more zeros than poles, probably rarely happens. So we know that our root locus begins at poles of g of s and ends at zeros of g of s. And if we have as many poles as we have zeros in this case, then our problem is pretty much solved. We know that the root locus will somehow start at these two things and end up over here. But what if the number's not equal? If the number of zeros is less than the number of poles, we'd still have paths that start at all the poles. And some of those paths, the ones that don't have zeros to match up with in the immediate plane here, would tend out to infinity. And they would tend out to infinity along, they would tend to some asymptote as they move out to infinity. And that asymptote would just be a line that starts somewhere on the real axis and heads off in some angular direction, right? So how would we find the point? So if we have that situation, the two pieces of information we need is where our asymptote connects to the real axis and what angle it lies at. We could have multiple asymptotes too. See that? So if our number of poles is not equal to our number of zeros, then this is how we get those values. So this sigma A, or delta A, this will be the point on the real axis, and just a number value where the asymptote starts. So this would be equal to the sum of the poles, sum of the value of the poles of G of S, minus the sum of the values of the zeros of G of S, all of that over the number of poles minus the number of zeros. All right, that's simple enough, right? So yeah, and what else do we want to know? We'd want to know, we know where the asymptote would start. We'd want to know what angles they leave at. Now, if we required 2 or more asymptotes, they would all start at the same point. They'll all leave at different angles, as we'll see here. So the angles they leave at would be 2 times n, let's see what, plus 1 times pi over the number of poles minus the number of zeros where n here is just integers. N would equal 0, 1, 2, and minus, and negative integers, all integers. So what we would see is that, so if we had, say, 2 more poles than we had zeros, we'd require 2 asymptotes, and we'd see that there's only so much we could vary n before we just started repeating our asymptotes. We'd end up with 2 asymptotes if we plugged the correct values in. So kind of wrote those down just for reference, because they're really not applicable to this problem, because as we see, the order of our numerator is equal to the order of our denominator. We have zeros to match up with all our poles, and we really don't have to worry about this, but that's useful for most other situations. Okay, so let's see if we can sketch the root locus here. So we know that there's going to be 2 separate branches. We know that the behavior has to be symmetrical about this axis. We know that this little segment here is part of the root locus, and we know that the root locus is going to start from here when k equals 0. Our branches, our 2 branches, will be there and there. And when k is equal to infinity, they'll somehow end up over here. So let's see if we can figure out a way that that all works out. So if we're here and we're here, but we can't stay on the real axis, right? We have to get over here somehow. Our branches would have to break away from the real axis and then stay symmetrical after that. So let's see if we can draw that. We could go, one would start here. I'll draw little arrows, what they're doing as k increases. So at first they'll start moving towards each other until they meet at some point and just can't go anywhere else, and they'll break off the real axis. And remember, we have to maintain symmetry now. So we have these paths moving, and they have to do the same thing. So at this point, we know that this point right here, or this path right here, has to end up here. And we know that this one has to end up down here. And we know that it's going to take some kind of curved shape. But without a computer, we don't know too much about the exact shape of that curve. But for our purposes, we're sketching, so we're gonna just roughly estimate that this would go something like this. So as k varies from 0 up to infinity, this path kind of gradually moves like that. And to maintain symmetry, this path would have to gradually go like that. Now, Okay, so as we see here, we had two moving towards each other, and then they broke away. Which one is which is really kind of not important. There's a couple more things we could figure out mathematically about this root locus. We'll do that in the next video. We could kind of refine, we can figure out mathematically exactly the point on the real axis where these break away like this. We'll figure that out. We could figure out exactly where it crosses the imaginary axis here. Why would that be important? Because let's keep in mind what this is actually plotting. These values, little points on this line, are the poles of this closed loop system as we vary k. So if we keep increasing k, we get to this point, we break away, and we increase k so that we get to this axis and just barely cross it. What does that mean? We know that our system becomes unstable once our poles end up over here, right? So a pretty useful thing we can get out of the root locus is where that happens. What values of k cause this to cross over into the unstable region. We'll figure that out next time. But yeah, for now, this is more just about the basic rules of drawing this root locus. And that should be good for this week. All right, thanks.